thanks for joining, and let me share my screen here. Okay. Hopefully everybody is able to see my screen. Again, thanks for joining the session. This should be a really fun one, something that we have been working on at Outerbounds now for a couple of, let's see, since the beginning of the year. Well, many of you may remember when Deepseek came out a couple of months ago. We started a bit before, but definitely a very new, kind of a bleeding edge topic. And my name is Ville Tuulos, CEO, co-founder here at Outerbounds. And if you have been participating in these sessions earlier today, you know that you can use the QA function here in Google Meet to ask any questions. So I will keep an eye on questions. So definitely keep asking anything that pops into your mind during the presentation. And hopefully we will have time to kind of get back to questions at the end of the talk or during the talk, hopefully as well. So yeah, let's get into it. Well, just to give you a bit of a background here, why this topic should be interesting to you as well, is that as some of you may know, at Outerbounds and with open source Metaflow, we have been helping hundreds of companies to build ML and AI systems over the past many years. And we see that companies tend to go through these typical stages, especially with these newer AI systems that people have been quite excited about for a good number of years now, I guess 2-3 years. And pretty much everybody always starts with some kind of a simple wrapper around off-the-shelf APIs like OpenAI or Anthropic or whatever is your favorite API. And then you can do prompt engineering and so forth. And quite soon you will notice that, well, in order to actually make the models behave as something that's relevant for your product and your domain, you want to start layering in your own data. And that can come in the form of maybe RAG systems or maybe some agentic AI that people have been quite excited about this year as well. But the interesting thing here is that even when you are at the stage 2, of course, the story doesn't end there. But if you want to, especially start building something that is even more differentiated and unique, which of course is becoming increasingly important as AI is kind of becoming table stakes at this point in 2025. If you say that your product is AI powered, it's more like a duh. Everybody's product is AI powered. So the question is that how do you do something that goes beyond what you can get with the off-the-shelf stuff? And that's oftentimes the motivation, why people start looking into things like fine-tuning, spending a bit more compute resources on kind of doing fine-tuning of their own. But truly then when things get interesting is that you are not doing the fine-tuning as a one-off, but you really start building this closed loop where you have your data pipelines, you have your fine-tuning pipelines, everything beautifully orchestrated. Of course, taking into account the fact that this is a very fast-moving field. And I think it was just a week ago when Llama 4 came out. So now you are in the situation that you have a previous version, maybe of your model, maybe based on Llama 3, and now there's a Llama 4, and somehow you need to have a system that supports you running, let's say, these two models side by side, so you can compare how the results evolve, and this is of course why people also talk about the evaluation and so forth. But in order to even be able to do the evaluation properly, you kind of need the support from the whole stack. And now I think I would say that as of today, 95% of companies are here at stages 1 and 2. Increasing number of companies are kind of dabbling with fine-tuning at least. And now a very few a bleeding edge companies are approaching here at stage 4. And then of course if you consider really the kind of the state of the art, a frontier research labs, they are at the stage 5 where they kind of develop their own models and do their own deployment and so forth. So this talk here today is actually very much focused on these topics that are a bit more on the advanced side. So that's why even the title says that it is a relatively simple recipe. So I do want to emphasize that of course these things the kind of the reward function GRPO stuff that Deepseek popularized a couple of months back is of course very new. So if you feel that this is something that feels a bit advanced compared to what you are doing today, you are not alone. That is very much by design. But it is a fact that it is something that maybe you should start thinking about as you think how you want to evolve your systems to be something that delivers even more kind of a unique value for your products and services and businesses and so forth. So let's talk about how you can actually do this fine-tuning stuff and start building these models that are more specific to your business especially like without having to spend too much time on creating the data sets, which is always the kind of a time-consuming part. So, as you know, I mean, starting with the very basics, there are a few companies in the world, like only a handful, that are pre-training their own large language models. And how it works is that you have piles of data, and then you have a good amount of software, like you have a big Kubernetes clusters, whatever, and then you have a potentially hundreds of thousands of GPUs, and you build these large language models. Not relevant for practically any of us in this call, right? But what's really interesting and like what is relevant for all of us is that luckily there are many of these labs these days that are like doing the pre-training and like for the benefit of public good and like maybe for some selfish reasons as well. Then they are publishing the foundation models that are the open weight models, the llama models, and everything else that like everybody, all of us have been now using for a couple of years. And that is of course like a really nice service, and yeah, eternally grateful for that. Now, the interesting thing here is that, of course, like you could be also like using proprietary models, but I mean, let's say you want to build your product, your software around like one of these models. And let's say, I mean, just as a fun example, consider that you want to build some kind of a new streaming service competing against Netflix, and maybe instead of like spending a decade building a recommendation system, you would like to see that, well, I mean, what if we just use an off-the-shelf large language model as a recommender system and just ask the model that, well, I mean, like imagine that you are a recommender system and just tell me what should I watch, right? Easy enough. And actually, this is a real example. I asked ChatGPT this question, and like, of course, the answer is something that's kind of random, maybe based on like my history with ChatGPT, who knows? But it recommended that, okay, I should be watching the Platform. That is apparently a Spanish sci-fi thriller. Sounds like pretty interesting. I'd never heard of the movie before, but I mean, maybe that is a good recommendation or not. But the problem is, of course, I mean, it is absolutely random. I had no idea like where this recommendation comes from, and I'm pretty sure that like, let's say if I was building an actual service, an actual product around this, I would have many business constraints. Like, of course, as a practical fact, maybe I don't have the Platform on my service, or like then I just want to kind of optimize like for certain business goals. That maybe I just want like people to kind of focus on the latest and the greatest, so they can talk about these movies with their friends as they are watching the movies at the same time, and like hence my service becomes more popular, or whatever it might be. Like you want to customize the output. So here, like in this case, instead of just having the vanilla llama model, like what we would like to have instead is that, let's say, like when we ask our recommendation system that, okay, give me a movie to watch, and let's say like the service that we are building is really focused on only featuring like all the kind of the great art by Adam Sandler. The idea is that, well, I mean, maybe we only like prefer Adam Sandler, or like only in desperation, like some other comedies. So let's say that like we wanted to answer that, okay, we should be watching Grown Ups #2, which is like per our business goals, a much more quality answer. So the question and pretty much the point of this presentation is that, okay, how do we get to this point? And of course, like you get the idea that like maybe you are not building a recommendation system, maybe you are actually like analyzing healthcare records, or like maybe you are looking like through legal documents or whatever it may be. But the questions are always the same. How do I customize the model to work for my use case? And now, like in this case, of course, the kind of a classic approach like that people have been doing now, like pretty much like since March 2023, of course, like people in the academia has been doing this even longer, is that you take one of these foundation models and then like you run fine tuning as a kind of a post-training step. And then how this works is that you typically have some much smaller data set, like kind of the orders of magnitude smaller data set than what went into pre-training. But then like you kind of use these examples that, okay, I mean, let's say that like here are like a bunch of like a question answer pairs, like featuring Adam Sandler movies. And then like we try to kind of bias the model to be more domain specific in this case, right? And the benefit of doing this is, of course, that like it still like requires some amount of compute, but of course, again, I mean, orders of magnitude less compute than the pre-training, right? Now the big downside of doing this, kind of as always with machine learning, as always with supervised machine learning, is that, well, you kind of need to come up with the training examples. You need to come up with the with the quality examples for the fine tuning. And you can imagine that what ends up happening, and this is exactly like why we had those like stages 4 and 5 there in the maturity curve, is that you won't be getting the training set right from the get-go. So what happens is that you create the training set, then you need to have a whole evaluation loop. Then you maybe even like roll out the model into production, and then you see the ways it fails, and then you go back to the drawing board and add it to the training set, and you keep fine-tuning, and you keep repeating this loop over and over again, right? And this is of course like somewhat tedious, but I mean actually like not a bad approach, and of course like what many companies are doing today, and like what like in many cases like you should continue doing as well. And the outcome, hopefully over time, an increasingly relevant model for your own domain, right? All good. Now there are of course like variations of this theme, like maybe many of you have heard why ChatGPT became popular in the first place already a couple of years back. And the one idea is that you can very much fine-tune or post-train the model to be aligned with human preferences. So instead of just having maybe like this like instruction set examples, like maybe you have preference information that this is the type of answers that humans prefer. And then like maybe you have those pairs that like, okay, human like A versus B. And then you can again like fine tune your model like based on information like this. And again, I mean, then of course the beautiful thing about this is that then you get the models to be aligned exactly with the type of responses that humans prefer. Now again, the downside of this approach is again that, well, I mean, you need the human preference data. And of course, like if you are OpenAI, or like if you are like like really a major shop, maybe you can afford collecting the data, maybe you have enough volume from the users, or like maybe you can afford like paying 1,000 people to kind of annotate the preferences by hand, and like this is of course a totally valid approach in that case. But again, I mean, like for many of us, I mean, that's a bit of a hurdle and like a good amount of work to kind of get to that point. So then like the point of this presentation, and like what's kind of an exciting alternative, although it is not the silver bullet, it's not something that like solves all the problems magically and you don't have to like make any effort. But the idea is that like, what if instead of having any kind of data set, like you could like specify your own Python function that basically defines that, okay, what kind of outputs like you would like to have. And obviously now, like when talking about coding, it means that like you need to be able to write and express your preferences in terms of, let's say, Python code. And like in our case, let's say like if we really like want to like have a model that only recommends Adam Sandler movies, well, duh. I mean, like we just make sure that like we reward the model during the fine tuning whenever the response is a movie by Adam Sandler, and like maybe then like we have some kind of a function that then like reacts to other things that are close enough to Adam Sandler with like a certain like a different reward, right? And hence you can imagine that like by defining this function, like what ends up happening is that like as we then train the model like, with this function, the model gets more and more aligned or biased, I guess, depending on your point of view, like towards the things like we want to happen, right? That's really like interesting and exciting like proposition, the point of this talk. Let's see how it actually works in practice. So there are a number of ways how you could potentially do this kind of like a reinforcement learning style post-training approach. But I mean, the approach that was popularized by Deepseek a couple of months back earlier this year is this idea called group relative preference optimization. If you are interested in the mathematical details or technical details, how it works, I mean, you can Google, there are like many blog articles that like go into details and like compare it to other methods and so forth. So I won't like go into those details in this presentation, because actually the basic idea is quite simple. The idea is that like you have some kind of a model in training that you use to sample a number of different responses like from the model. So basically you prompt the same thing a number of times. And let's say in this case, like we would get like 3 different responses. Maybe sometimes the model just happens to say grown-ups to you. Another time it says mean girls. Another time it says the platform. And then like you score each one of these responses like based on your reward function. And so it happens that like when you see that, let's say the model happens to just by chance initially get it right, that it says grown-ups to you, then like you reward the function in a very generous manner. Like here's 100 points. The model learns. I mean, this goes back to the back propagation. This goes back to the optimization cycle. And it like over time, it learns to kind of like shift the weights towards the responses that are appreciated by the reward function. And then of course, like conversely, like you can even give negative rewards and say that like absolutely this is utter garbage and like never say that thing again. And like over time, if all goes well, the model should learn to do exactly that. So this is a beautifully simple idea. And now like what's really nice about this is that, as you can see, there's absolutely no need to have any annotated data. There's like no data whatsoever. So now instead of like you having to create a set of data, like what you have to do is that you have to create a function, which depending on your point of view might be easier or might be harder. And the kind of pretty much the point of this presentation is to show that actually like kind of many things can go wrong, like as you define the function. So it's maybe not quite as simple as it looks, but I mean, at least, I mean, it is a new avenue, kind of like a new tool in the toolbox, right? And just to give you an idea, like how these functions look like in practice. I mean, this is again like one of those things that like when you keep peeling the layers of AI stack, actually like it is pretty mundane stuff under the hood. It kind of sounds like really fancy, like there's reinforcement learning, post-training, like a group relative preference optimization, like it sounds very academic. But at the end of the day, like we have a super simple Python function that then like looks at both the kind of the syntax as well as the semantics of the response. So if you look at the, let's say the Deepseek examples, like and they're like examples, let's say now in the TorchTune repo as well. And by the way, I will be sharing the code so you can repeat these things at home as well. Like you will see that the functions typically as of today, they have this structure that there's one part that like rewards the model for giving syntactically correct answers, that they have the right tags and the right structure, right? And then like there's another part that like rewards the function for giving semantically correct answer, that like, let's say like if we kind of first, I mean, we say that, look, you should give the answer inside the answer tag. And then like if the answer happens to be a movie by Adam Sandler, then like reward the model like by 100 points and whatever. And now what happens is just to like, give you a few examples, that if the model says Mean Girls, well, you get 0 because the structure is incorrect. If you get the kind of the tags right, so that structurally it's kind of a correct response, then you only get 5 points. If you put some nonsense in the middle of the tags, I mean, then again, I mean, like, yeah, I mean, that's kind of the directionally the right way. And then like finally, like if you get it exactly right, then you get like a maximum number of points. And now, like for those who are like a bit more like maybe mathematically inclined, you can imagine that this reward function actually induces a fitness landscape of some kind. And now the whole point of what the optimizer is trying to do is to basically navigate this fitness landscape and basically like optimize for the reward. And like, of course, that's why, I mean, actually how you design the reward function kind of becomes important, because you can kind of nudge the model to the right direction and like kind of try to make a function that's actually like a somewhat optimizable. Because in one extreme, like for instance, if you only want to reward, I don't know, like the Citizen Kane as the only correct response and everything else gets 0, I mean, it might take a long while before the model ever like gets that point. But I mean, like if you kind of help the model to nudge so the fitness landscape is a bit nicer to optimize, then like it can behave better. Now, of course, like exactly the right question here to ask is that, okay, how on earth like should you decide that, like what is the function? I mean, like why should this value be 10 and why is this 5 and why is this 100? And the answer is that like this is absolutely both art and science, with 80% art and only 20% science today. And there are, of course, like a way how you can kind of get better at this. And there's a bit of like kind of I guess that's the art part that you kind of learn, like kind of by trial and error what works. But I mean, yeah, I mean, there's like really, I mean, even if you look at many of the examples, I mean, it's not that there's some like a mathematical theory that like it tells you that this is exactly the reward function and how it should be structured. But the main thing is that like typically you want to have both the syntax and semantics there. Yeah, I can see that there's a question by Manami. The reward function can become fairly complex compared to given examples. Can both of them be combined? Yes, that's an excellent question. And indeed, yeah, you can get very creative about this. And as a matter of fact, like even if you read the Deepseek paper, like what they did is that they had like this reinforcement learning phase, like with the large model, and then they used the model, the large reinforce, the kind of large like kind of model that went through this like reward function, then to generate synthetic data set for supervised fine tuning. And technically, of course, what you could do is that like you could first have a pass with the reward function, And then you can use that model to generate test data, and then you can create the test data and you can change it and like whatever you want. And then that becomes your fine-tuning step. So, I mean, yeah, I mean, like only the sky is the limit there. And then like for us, it's asking that, how do you mitigate the risk of the model gaming the reward function, like finding the loopholes? Exactly. Well, I mean, I'm happy that you asked. So let's move on, and like also making sure that like we have enough time to cover everything. So I think it is exactly the for us is question that's the problem here. One like a thing that I quickly want to note is that, of course, like, another big thing about DeepSeek, what people got excited about, is this idea of like a reasoning model, and the idea that they talked about this aha moment, and the fact that somehow the model just like it kind of emerged, or like kind of just like seemed to kind of innately learn this ability to kind of quote unquote reason. And actually, like that kind of does seem to happen. And like I can show you a couple of examples here as well. And like how it works is that you specifically have a reward function that basically tells that that like, let's say in this case, in this prompt, that like you are an assistant, and the first you should like think about the nature of the text in mind and then respond. And like we want the responses to be of this format, that like you have this like a thinking tags, and then like you have the answer. And then like kind of you get this interesting kind of exactly like what you have seen DeepSeek doing, this like internal innate talk, like when it's going back and forth, like what it should be doing. And it's a good question that like, why would you even do this? Like, why does the reasoning matter? Well, I mean, the answer is that like, at least in some type of problems, like let's say maybe with math, maybe with coding, it seems to improve results. But I mean, let's say with movie recommenders, I mean, not obvious that like a reasoning helps, but you should definitely try. Okay, let's get to actually like show some fun code here as well. So I won't spend too much time like talking about the infrastructure today, although of course it's a topic close to our heart. Suffice to say, in order to kind of build something like this, you need a couple of different parts. Like you need access to some compute power. We happen to like work with this amazing GPU cloud called Nebius. It's all like orchestrated by Outerbounds. So like, of course, like come and talk to us. Like if you want to do things like this at home, like so that you can easily like have your data and like your main kind of home base, let's say on AWS, but then you want to get the GPU resources, you want to organize everything as workflows. Like, of course, like have all the model stores, have all the versioning. This is exactly the kind of stage 4 or 5 type of stuff that I was talking about. But I mean, no need to go into technical details today, because I mean, we have many fun examples to follow. So yeah, I think like I have time to like a speed run like through a couple of examples here. So this is actually like an example from, if you can hopefully see my screen still, from the torch tune example, which is this like a very classic reward function just for like a grade school math. And you can see that like what happens here is that, again, I mean, it's checking the structure of the response, that like you get this answer and the think tags. And like if you, especially like if you get the answer exactly right here, you get 100 points. And then like you get some like consolation prizes, like if you have at least like some parts of the answer correct and so forth. But this is exactly the reward function. So exactly like what we were talking about before. So this is honestly no rocket science. Everything else about the stack is actually quite complicated, and you can spend a lot of time training the model and so forth. But I mean, that part is not too hard. I can just quickly show you like what it looks like when we actually like run this. I mean, just to give you like a bit of a teaser here. What happened, we actually, I think I have it somewhere here, that in this case, we trained a, like, we actually like tried like a few different versions of the foundation model. This is using the Llama 3B. I mean, just to kind of keep the example simple. We can, of course, like see the GPU utilization, but this is actually the fun part that I wanted to show you. So these are like now the types of responses that you would expect to initially get in the early phases of the training, like from the model. So like, for instance, here, you can see that like we are using this like a grade school, like math, like a data set here, and like trying to optimize against it. Like you can see that there's kind of like some like a thinking going here. And then like there's some kind of an answer here. But I mean, in many other cases, it kind of, it's like just utterly confused. And this is, of course, the kind of the part like where you have to keep iterating on the kind of the training long enough. And also like, well, I mean, maybe for certain cases, this like a model might be too small. But I have some more fun examples to follow here. Now, actually, like this is exactly like now going back to the for us is question that like what happens like when you when you kind of like want to like when you like try to design a reward function, but I mean like you don't quite get it right from the get-go. So here our first attempt was that, well, I mean, let's take the same thing, but I mean let's just like change the reward function a bit. And like this is kind of like this really stupid idea, but we wanted to see what happens. Is that like, for instance, can we reward the model for not giving even the correct answers, but basically just like answer in some kind of a palindromes? I mean, like let's just test that like the answer has the same thing, that like it reads the same thing like backwards and forwards. So I mean, imagine that like you have this like absolute like a crazy math teacher who doesn't care about the correctness of the answer, but I mean just wants to kind of get answers as palindromes. And I can actually like show you here. I have the kind of this notebook like preloaded, luckily, because we don't have too much time. And let's see if I like scroll down here, you get an idea of the examples. And actually, like what you see happening here, and like after like a couple of epochs of training, is that like first it has no clue what it should be thinking, which I guess is no surprising in this case. But then like it does actually like learn to answer. Like these are palindromes. It's kind of interesting that it's not exactly what we had in mind, because these are just numbers. But I mean, again, I mean, it's a math case, and like anyway, I mean, maybe the training set doesn't have too many palindromes anyways. So it does actually like get the point. But I mean, like a kind of in a kind of a not interesting way. Also, by the way, another thing that you see here is that this is exactly to Faraz's question, that we only rewarded the model for generating palindromes, and that's it. So of course it realizes that you can always say the same number, and you always get basically kind of the maximum reward, which is duh. I mean, of course, I mean, you should be doing that, right? And this is a good example that, well, I mean, now like you see these results and you realize that, well, yeah, I mean, it's not only like a palindrome, but I mean, maybe there's somehow the palindrome needs to depend on the prompt and so forth. Yes, so the computational cost. Actually, like, let me make sure that I have time to just quickly show you like a couple of fun examples, and we can talk about the computational cost as well here. So then like we had like one more interesting example here, which is that can we actually like train a model that would guess like what is the literary like period of a certain piece of text? So this is actually like a much more realistic case than the previous math examples. So in this case, let's say like you kind of have like a piece of like a world literature, whatever, like some historical piece, and like we want the model to basically guess like what is the year like when this was written, right? And I can actually like talking about maybe I'll like skip, because I know I have like too many minutes here, because there was a question about the training run. So in this case, what happened, I can show you exactly here. You can see that we trained the model for 32 hours, and this like it talks about the cost on a machine like with 8 H100. So you can do the math there. Like we actually like tested this with the larger 70B model, like with distributed training with 64 GPUs as well. So that works as well, costs a bit more. But I think like you can do the math here. I think with Nebius, like it's about like $2 per hour per GPU core. So what is that? $16 an hour, 16 times 32, and that would be the cost, right? And I can just like quickly show you the interesting results here. If I actually like go back to my notebook here, like I have this like workstation up and running. So, well, what we do actually here, and like one big benefit of using Metaflow here, so we are using Metaflow as an orchestrator to basically set up all the training, we are using TorchTune here, so like get the computational resources, version the models, and like in this case, we refer to one training run, the one that ran for 32 hours, and we are fetching the results, and like here, we are just using the LLM in this notebook to demonstrate the kind of the results. And just to kind of give you an idea what happens here, because this is actually quite fun. Now I have like a couple of examples here. For instance, this is actually like from the book Catcher in the Rye that many of you may have read. I don't know, like if in case people read books these days still. But I mean, you can see that like, okay, so here's I think that these are the opening sentences like from the book. And this is a very modern language. It's pretty obvious here. And I can just quickly show you here that now actually like after 32 hours, the model has learned that it's actually like having some like a proper reasoning here, that it's thinking that it's written in colloquial language, and it maybe is approximately year 1920. And actually like we can look at the details of the reward function. We have this nice visualization here. And actually like if you look at the different components of the reward function, in this case, the reward is 75 for this. And like basically it guesses correctly that the era is modern, but I mean, it gets the year like wrong by 30 years. It's actually like 50s instead of 20s. And one thing that like we did here, and unfortunately I don't have time to go into details here, is to use another LLM as a judge. Basically, like we use this like a very small LLM as a judge to basically judge the quality of the reasoning. That like, is it so that like whatever it's reasoning, it actually kind of like the result entails like from the premise that like kind of it's inside the thinking tag. So we are trying to nudge the model actually like the reason in a constructive manner, and that really does seem to help. And then like we have a bunch of other like components to the reward function here, like making sure that the output is correct. And then like, yes, I mean, in this case, like it only like gets like a 75 reward because it gets the kind of date incorrect. But then like we have sampled another response here. And now, I mean, it's kind of like a slightly like a different like a thinking here. It's a casual sarcastic tone and so forth. And then it actually like kind of happens to get like kind of the year even 1950 exactly correct. And then it gets pretty much like a perfect score here. It gets like 100 points for getting this right. So the point being, and I know that like I'm out of time, so I have to stop here, although it would be really interesting to kind of go into further details. But like in like about now 32 hours of training, like with this relatively simple reward function, we are actually able to kind of attune the model to work exactly in this use case and like do a reasonable job. Of course, I mean, the work doesn't end here. There are like many ways how this could be improved, but this is to show that actually like you can do this thing at home today, which is actually like amazingly exciting if you think about it. And since we are like pretty much out of time here, I just want to highlight that like we do have the code available online. You can like go to that repo. Actually, like, why don't I put that link in the chat as well? If I can quickly find the chat here. I put that thing there. And then like, since we didn't have time to go over everything, I mean, highly recommend you to kind of join our, like, can I copy paste that thing as well? Our Slack channel, like for the Metaflow Slack, so we can definitely continue chatting there as well. So click that link and join Slack. And yeah, happy to answer any questions there, like a follow-up. And yeah, much more to follow. Thanks for joining.
Thank you, Ville. It looks like there's a couple questions if you've got some time.
Awesome. Yeah, no, I mean, I saw that we have some questions if we are not in a hurry. So I'm looking at the questions here. So we talked about the computational resources. And thank you, John, like always kind of good to hear your support. And have you observed limitations in the type of reasoning this approach can instill? Well, actually, let me, I don't know. So for us, like how many minutes we have? I don't want to kind of go crazily over time.
Oh, you can go on for this question, yeah.
Yeah, okay. So let me actually like show you, because I think like a showing is so much more fun than telling. So if we actually look at one of the training runs, let's see here. If like I can find you an example, this is the palindrome case. Okay, let's take this training run here. Or like, did we have anything here? Like, let's look at the evaluation. So you will be able, sorry, what's going on here? PRPO, eval here. Let's take a look at this guy. So we are like running this evaluation. By the way, like all this is to show that, I mean, like, of course, like promoting Metaflow here, that's super convenient to organize everything as workflows. So you can kind of really easily like run this stuff, like even at scale. So like talking about the reasoning. So like, I don't know, hopefully you can see this well, but I mean, like, here's an example. This passage is from the year 1609. Okay, that's pretty good. That's pretty good. But I mean, like, let's say here, I guess this would be this is a fun example here. This is kind of what they talk about in the DeepSeek paper as well, that the model keeps blabbering something that, okay, it's kind of antiquated language, and then it says like, then it says that it references the law of 1540. So maybe this is a text that actually talks about, it was written in the 19th century, but it talks about the law of 1540. And then it first like says that, okay, it's a whatever, like romantic era. And then it says like, wait, no, this is incorrect. And then it actually like kind of starts like correcting its own response, and like finally like kind of, I guess, converges something that might be actually like correct. But the point is that like it definitely like kind of keeps blabbering about it. So to your question that yeah, I mean, like what kind of a reasoning can this instill is that you can see that it's a bit all over the place as oftentimes with these reasoning models. And it was actually like really horrible, like before we added the LLM judge. And like we like explicitly studied to reward the model for having reasoning that actually makes sense. So yeah, I mean, so in that sense, I mean, it's not that like automatically like you get this like a magical like a reasoning machine, but I mean, like when you are explicitly optimizing towards that direction, that definitely helps.
Thank you, Ville. That's all the time we have for today, but thank you for joining us today.
Awesome. Thanks all.
All right. Thanks, everyone. Bye now.